Welcome. Let me say a little bit more about sectional curvature. I made experiments and it looks as if sectional curvature, which has been defined by Ishida and Higushi, works very well. So to repeat what we did in the past, we work with a finite abstract simplicity complex, which is a Q manifold, dimension Q, and we have a notion of facets, which are the maximal simplices. We also have, for every hyper facet, which is a kind of a wall, we have just exactly two facets which are containing it. And then we have a dimension, one dimension lower, we have the bones, which play an important role. And the bones are, in the three-dimensional case, just edges. And we are looking at all tetrahedra which are hinging on an edge. So this is very, very nice. And this nice toy here also can explain a little bit the geodesic flow. So what we do in the geodesic flow, we have a frame, which means a total order on a simplex. This defines us then for every point, gives us a dual point, and now we can continue like that, and we can build a geodesic. We can build a geodesic chain, and this geodesic chain has zero curvature everywhere. From 2011 about Gauss-Bonnet-Chern, which is just Gauss-Bonnet in the case when we have a curvature which is supported on zero-dimensional simplices, and we can also locate the curvatures on the Q-dimensional simplices, which is the facet curvature, as long as the simplices, the maximal simplices, cover the entire manifold. For a manifold, of course, this is the case, and then what we can do is we just take all the energies and push it to the facets, and what we get is a curvature which, in the case of two dimensions, has been considered already in the 90s of the last century. And what happens is the dual plays an important role. The dual is can be, first of all, it's a graph which just contains the maximal simplices as vertices, and two are connected if they share a common Q-1 dimensional simplex. And so in this case, in two dimensions, we are very much interested in the two-dimensional case because we want to define sectional curvature. We want to define a curvature for geodesics which go in a define a two-dimensional sheet. And that always looks like that. All the geodesics which start here are not in the frame bundle, but are in the dual graph the same point. So we have always this structure locally, and we can use this local structure to define curvature. So it's a second order curvature in some sense, and that makes a lot of sense because also curvature is second order in the continuum. And it also behaves nicer than the Leavitt curvature or the curvature on vertices, which for positive curvature manifolds is often negative at some points. So this is really behaving nicely, and first experiments show that this is really a good curvature, and it gives the right notion, and it satisfies in two-dimension Gauss-Bonnet, which is kind of nice. So this is the formula for two-dimensional CW complex. And then once we have a sectional curvature, we can define a Ricci curvature, scalar curvature. We can define the Riemann tensor, which is just all the possible curvatures which we have at the point, and also have a notion of like Hilbert-Einstein. First of all, we need, of course, to study that much more. Here, just one simple example. We take the smallest three-dimensional sphere which exists, which is a 16 cell, which is one of the three-dimensional spheres, and we have the dual is the tesseract, which is a tesseract is an object to and we can now look at the geodesic flow. The geodesic flow is pretty boring here. Every geodesic has length, orbit has length 8, and we can also look at the geodesic sheet. A geodesic sheet is just a cube here. So it's a two-dimensional CW complex, and we can look at the curvature. Sectional curvature is 1/3. So you add up all the sectional curvatures over the cube over this geodesic sheet, you get the Euler characteristic. But it's not the Euler characteristic of the whole manifold. The whole manifold has, it's a 3-manifold, or an odd-dimensional manifold has 0 curvature. So yes, so that's to be continued, and that's it for today.